Might be a long talk. Or a short one, I don't know, we'll see. Yeah, welcome everyone to R-CCS. Sorry, I'm wearing my happy coat from this conference last week, so I thought I'd come in that one. And because I was like organizing the buffs over there, and it was actually a very fun conference. So if you want to attend next time, Singapore, or the other one as HPC Asia will be in South Korea. And then hopefully the year after it will be merged again. Okay, scientific benchmarking. Why do we need scientific benchmarking? If you have any questions in between, just let me know. Raise your hand, don't worry. Why do we need scientific benchmarking? Basically, with the increase in like various computational patterns like machine learning, but also cryptocurrency and others, we have seen an explosion in hardware choices over the years. So, for example, cryptocurrencies, they started out on CPUs, moved to GPUs, then FPGAs, then ASICs, and now the majority of cryptocurrency is mined on ASICs. On the machine learning side, similarly, people started out on GPUs, not really CPUs because they straight went to GPUs. But then various accelerators came into market, Samba Nova, Grok, and so on. They're all coming out with their custom hardware. And we as HPC centers kind of have to make sense of all of that and figure out how to integrate those types of chips into our systems, because we have given up, unfortunately, building our own decades ago because it became too expensive to do so. So we are seeing essentially like increases of specialization in all fronts. So we have like specialized phone chips, FPGAs, CPUs. Like FPGAs even make their own way into the CPUs nowadays. So Intel bought an FPGA company, AMD bought an FPGA company. I believe it hasn't really materialized too much, except that they are starting to integrate like NPUs, neural processing units, and they are a little bit like FPGAs. But it will come more and more, probably as Jeff alluded to a couple minutes ago. Similarly, we see an increase of programming languages. Jeff also mentioned CUDA. We have the alternative HIP, one API. Then you have Cocos Raja, which is a little bit more sitting on top and trying to orchestrate across them. But then you have like Rust, Julia, Python, all sorts of languages. C, Fortran, yeah. And then on the workload side, things are becoming more complicated. Traditionally, you compiled your code. It was a single binary. You had an input. It ran for a while. It had an output. But nowadays, it's becoming more problematic. The majority of ML stuff and like science stuff is, or people are trying to containerize them because of the software complexity. So you have to try to run containers on your HPC system. We have a lot of big data. Not traditionally, it was like a couple hundred bytes of like input data sets. Now it's like terabytes, petabytes of inputs. A lot of workload will be chained together where you have pre-processing, post-processing, and intermediate stages. Think of genomics workloads where you have to split the files, you process the files, in the end you throw it into the next, and then you potentially send it off into an ML workload. And things as a service, so LLMs as a service can happen, or in general, like you can send instructions to certain hardware, for example, quantum computers. So that might be more like an as a service situation, because they are at the moment very special for only unique tasks, and so we can't tightly integrate them as we would like with what we do with like GPUs, for example. So we have like a single one, the HPC system has to compute something and then has like a single thing, sends a quick instruction to the quantum computer, waits a little bit, and then brings the result back. So that's like the as a service style. And then we have topologies, one of my specialty from my PhD studies. It's essentially how to connect all of those big systems together. So there we have like HyperX, Slimfly, Dragonflies, Megaflies, traditionally more like cloth networks and like torus networks, what we have in Fugaku, for example. Yeah, basically, if you have such a gigantic sea of options, how do you effectively benchmark that, and how do you select the right architecture for your workloads and the right architecture for your future system becomes a challenge. So for example, we are doing that on a regular basis for the design of Fugaku Next, what we are like being tasked with by the Japanese government right now. And in general, you also want to do that just to compare different hardware vendors and see how they perform, and then maybe help them a little bit to improve their hardware, because you don't want to end up with a single hardware vendor. Otherwise, they charge you an arm and a leg, like NVIDIA does nowadays. Okay, so how do we benchmark performance is essentially a big question in HPC, but for that, we need to know what performance actually means. And that can be various many things, so throughput, response times, reliability, development cycles. I mean, like, you can define it as you like. What do people think? What would be an answer to that question? How would you define performance? Okay, so effectiveness, yeah, that's basically very similar to how many programs you can run at a given time, like in a day or something like that. That would fall under effectiveness, essentially. Yeah. So it basically, kind of all of them are correct. It basically depends very much on the context. So you can do performance in the sense of effectiveness. You can do performance. Do I have a? Yeah, slate. You can do performance based on like lowest energy consumption. How can you run the most jobs with the lowest consumed energy? Because you can like spend a lot of more energy by like just clocking your CPUs higher, but the application might not run faster, or it might run like very slightly faster, but it consumes twice as much power. So if your goal is to have the highest performance, in terms of like flops, for example, floating point operations per second, then you would clock to the maximum. You would overclock your chips. But then they also degrade, and then you have to replace them, and yada, yada, yada. So not the ideal scenario. But yeah, basically it depends always on your metric you choose and on your goal, what you want to communicate. Traditionally, most vendors go for the highest performance. So if you like compare CPUs, then they say like, okay, we have the most megahertz, we have the most PCI lanes, we have the most whatever, or our ML workload runs the fastest on XYZ. So if you look at like GPU vendors and specialized hardware vendors, they just say, we can do that many tokens per second. So like individual units essentially in the ML world. Yeah, so essentially what you have to do scientific benchmarking is you have to define what your goal is and what metrics you want to do. And after that, you can move on. If we look at, just as an example, CPU performance, then we see that a bunch of internal factors can define your performance. And for the CPU, it can be, as I already said, core frequency, so like, I don't know, 3000 megahertz or like 3 gigahertz. It can be peak performance. A certain vendor will tell you I can do that many flops per second, or I can do that much memory bandwidth per second. It can be influenced by the number of floating points units or integer units you have in the chip, depending on your workload. If you just have floating point units and no integer units, or almost no integer units, then most of your workloads will probably not work well, even so theoretically they could, because you're just like limited by the amount of integer units, because you basically have to do address calculation all the time anyways. So if you're under-speccing your integer units, you're kind of screwed. But then there are also other factors, like the bandwidth and the latency of the caches. So typically, higher bandwidth caches and lower latency caches are ideal, but not always. It depends. It depends basically on your workload. Yeah. And then we have external factors, not just internal factors. For the CPU, so it's like the amount of memory controllers you have to bring essentially data into your CPU. You have a lot of interconnects, either on chip, where you're going to the GPU or you're going to the whatever you need to do, like the storage device. And then you have like off chip in the HPC context, where you connect to other CPUs across the system, like Fugaku from one node to another. Additionally, factors are power and cooling capacity. So if you're running out of cooling capacity, for example, if one of the towers there in the back of the building fails, then we probably have to shut down a few racks, and then the performance of Fugaku will be slightly degraded. You can also have other external factors like system noise, also system environment factors. So if you ever try to, I don't know, run a game on your laptop and your browser was still open and playing a video on YouTube, then you will see that your gaming performance essentially drops. So those type of like OS noise can heavily influence the performance of a system, especially if you do parallel computing, because you kind of have ripple effects throughout the system. So if you have like 10,000 nodes and they all need to compute something and synchronize eventually, so you do lockstep essentially, everyone computes something, synchronizes, computes, synchronize. If something is slow because there was a daemon running on the system on one of the nodes, and everything will slow down because the synchronization has to wait for the slowest essentially. So all the other nodes, the 9,999 will be slow if one is slow. So you have to be mindful of that if you program, especially if you program lockstep on systems like Fugaku. Human factors can happen as well. Someone can trip over a cable or misconfigure something. If you have like a wrong BIOS switch or something else, then your performance might be down. I mean, like AMD and Intel nowadays, especially AMD, you can have different modes of your EPIC CPUs, depending on how the cache is configured. GPUs as well, you can like set them into different modes. Like overclocking can also happen, accidentally blowing up something. So there are human factors, and your own skills also matter, depending on how good your software is or how bad your software is. Okay, so in general, if we go to performance metrics, we want to define metrics as something which is easy to measure and easy to communicate. If you have a metric which is hard to measure, you will waste a lot of time, A, analyzing it, and B, figuring out if you have measured it correctly and what the numbers mean. So it should be very easy to measure. And because most of the time you want to communicate to other people, not just like for yourself internally, you need to easily be able to communicate. So, for example, tokens per second, very easy. If you have 20 tokens per second, then that's about the reading speed of a human. So that's great. If you have something like, I don't know, 20 bytes over the PCI bus per picojoule or something like that, it's like it's a metric, but it's hard to communicate to like decision makers, politicians in an elevator pitch. So you want to have something easy to communicate. So we have a few metrics like response times. So latency, it's essentially time to first token. You hear that a lot in the ML context. So if you asked an LLM a question, how long does it take until the first token appears on the screen? So that is response time. Throughput would be how many tokens I can get out of the LLM within the next 2 minutes. Then we have others like bandwidth, utilization, like how many cores can I simultaneously run on the system. Mean time to failure, for example. The bigger your mean time to failure is, the better, because it's less likely that an entire parallel job fails and you have to go less often into the server room to replace something. There are other things like load, speed up, and so on. And overall, you want to have something which is linear. So interpretability is essentially very important. So you want to have something which is linear. It grows based on a certain x-axis, whatever the x-axis is. You want to have something which is like easy to understand. It's important that it's consistent and hopefully not depends on external factors, mostly internal factors. Should be reliable and interpretable. So those kind of things are important if you define or if you want to set up a metric. Yeah. How do we evaluate those metrics and the performance is essentially the next big question. And there we have different options. One is the analytical model. So essentially you go at the specification of your CPU, for example, from Intel, and you say, okay, I have that many floating point units, I have that much of a clock frequency, I can do in every clock frequency that many computations with those floating point units. They are vector units, potentially in AVX 512 or something like that, then I multiply this by X, Y, Z. So in the end, you can calculate what's the theoretical peak performance of your chip. This is quite nice because you can do that relatively fast, but it is rarely accurate in practice. For certain workloads, it's relatively okay, but for other workloads, you will be way off with this type of analytical modeling. Then you can do computer simulations. So you do you write your own hardware simulator. I have worked on like network simulators, for example, where instead of building the real network, you just say, okay, I have bytes I want to transfer. I have a switch here and a switch there and a link between them, and I have to transfer that many bytes. And instead of transferring the real bytes, you just say, okay, I have a header which says where the bytes need to go, and I have a theoretical payload of a certain size. This will take, and then you add in latency numbers. For example, you say, okay, speed of light over the wire at a certain distance is that much, and I have a processing speed of the switches of, I don't know, 300 nanoseconds, and you want to know how long the message takes from one side of the system to the other side of the system, and you can simulate that. The good thing is you don't need the real system for that, and it's typically more accurate compared to your analytical model, but it can be extremely slow and it can be infeasible for a large system. So what do I mean with slow? We have done architecture simulations for CPUs. We wanted to know, we have a certain CPU and we want to upgrade that CPU with certain specifications. How long would a typical application run? What would the benefit of this upgrade be? So the real applications run roughly like 1 second. And the simulated applications run at least 30,000 times slower per core. So if you have more cores, it ran multiple times of those 30,000 times slower. So I ran simulations about 8 months. So I started a simulation and then I waited 8 months. And I checked occasionally, like, are they still running? If yes, great. If not, checkpoint restart, that was fine. And most of those applications should have run in real time in like a few seconds. So that's what I mean with like it can be very slow or infeasible. So that was single CPU simulations. Now imagine you have Fugaku with 150,000 of them. That's another factor of 150,000 you have to do in a simulated environment because most of the time you can't parallelize it. So it's like you're basically limited by CPU latency on a single system. And that would mean you have to wait 150,000 years to finish those simulations. Not feasible. You rather build a system and then you test on the real system. And that's why you have the real measurements. So most convincing, fast to do, but you have to wait for the real system to be built, which can be expensive or it can be cheap. It depends. Yeah. So those are the methodology trade-offs. So how do we compare system is now the question. So that was like, here are the metrics, here's how we analyze a single system, but then how do we do the real comparison? Because if you just analyze one system, it gives you one data point that's rather useless. You want to see if this system is better than this system. For example, if you have factors you want to study, you have 3 different CPUs from vendor A, B, C. You have different memory configurations of capacity, so your CPU has either 4 gigabytes, 8 gigabytes, 16 gigabytes, so kind of laptop specifications. You have different workloads, like you want to do Excel, or you want to do, I don't know, Adobe, and you want to run some ML stuff on your laptop, and then you can do different operating systems, like Windows, Linux, macOS. And you want to do a metric which is response time and price, or price. So how would you study that? How would you go about it? What would be your approach to find the best system in this case? Test all of them. Okay. There are slightly better approaches, and I will let you know why. So what you essentially proposed is what is called a full factorial design. Will be on the next slide. But so what you have to understand in this case is that the amount of combinations you have available can become infeasibly large because you have to essentially test all of those configurations. Sometimes they're impossible to build, and sometimes they are not necessary to actually benchmark. But like if you look at this like workstation example where you have, what was it? It was CPU, memory, workload, and operating system. You have 4 times 3 configurations. That means you have to run 81 experiments. Let's say every experiment takes a day. You're looking at 3 months of experimenting. Sometimes that's not a good idea. If you have to do additional experiments, it takes even longer because typically you want to do multiple tests to weed out any like outliers. Sometimes there is the cosmic ray hitting your laptop and something becomes slow for whatever reason. So you have to do multiple runs, and that can then lead to like 400 observations if you just do 5 runs. So it can be labor intensive. Sometimes it's not because you just set it up, let it run, wait for days, and then you come back. It's fine. It's not too labor intensive, but it's extremely time consuming. But yeah. There are other approaches where you do a simple design study and you just vary one factor at a time. So you start out with the most typical configuration and then say, okay, if I take this and I switch this out, what will happen? and you kind of make an educated guess. So for example, you want to run ML, then you take a CPU with the highest floating point performance because you know that you need DGEM operations or like something similar to DGEM operations for your LLM. You know that you need a lot of RAM, so you go with 16 gigabytes, and you take, I don't know, probably Linux because it has the most software and cheapest software available to you. But then you swap out CPUs. For example, you say, okay, maybe I can get away with the other CPU. So you take this initial configuration, change the CPU, test again. If the other CPU is slower, then you just discard the entire CPU lineup and you take the third one. And this would be the very simple design study. So you start with initial configuration and change one parameter at a time. If it gets slower with that, you completely discard this parameter and then you move on. It can lead to situations where you don't find the optimal solution, but typically you find a very good one. So it's very similar to how you do mathematical optimization with heuristics, where you get kind of stuck in a local optima, but you don't find necessarily the global optimum. So then we already had the full factorial. Not a good idea. Easy to set up, but it's, as I said, expensive. Sometimes you don't have all the configurations available, and you are at the mercy of like other factors, like external factors. There's something like fractional factorial design, where you also reduce the amount of experiments you want to run. And here you kind of subselect out of the full factorial one, reasonable configurations down to whatever you want to have. So, for example, you have different memory configurations, and instead of benchmarking, I should probably use the laser pointer, it's easier. Instead of benchmarking every single operating system for the cheapest CPU variant, you just do mix and match between workload and operating system to reduce how many experiments you have to do for the cheapest. And the same you do with the other configurations. So you bring down the configuration space with this fractional factorial design. So it basically saves you time and cost because you don't have to set up all the experiments. It's less labor intensive, hence less costly. You might miss a few things, but overall, it's a good in between the full factorial and the simple design. Okay. So now we have done, and we are done with our experiments. We have to analyze the data and interpret the data. And here, the most common way of communicating your experiment results is essentially with charts, graphics, because it's easier than just reading a bunch of text. So the aim is essentially to help the decision-making process. And if I show you two bars, and unless I'm cheating like some of the vendors out there, then you can easily see which one is better than the other. There are various chart types available, and it basically depends which chart you should use based on the data you're trying to communicate and with whom you're communicating. Sometimes it's better to use get rid of some of the data and use an easy chart like a bar chart, and sometimes you have to go with something more sophisticated like those timeline charts or 3D stuff. So this is a timeline where you have different processes and you see how they behave over time. This is a 3D version. Here's the bar chart, here the line graphs, like different timelines with Gantt charts and so on and so forth. So this is how you essentially then communicate with your decision maker, because your boss asked you like, hey, benchmark those configurations, which one is the best, which one should I buy? In this case, it might be easy to just like tell him like buy this, but if he wants to see the results, then it's probably easiest to just say, okay, I have my results on the x-axis, my configurations on the x-axis, and the performance on the y-axis, and you just have a bar chart, and then your boss can look at it and like, where's the highest bar? There, okay, I will buy this configuration. Okay, as I said, it kind of depends. You can like mix and match a little bit with like the different results and the different chart types. But overall, you want to make sure that you select a certain type for a certain thing. So if you have contiguous data, it's for example good to do line charts or line graphs. But if you have non-contiguous data, then it's a little bit weird, because you would see like strange spikes in your lines, and it doesn't make sense because in between there is no x value. You're just making up an x value and interpolating between 2 points. So typically you want to do like bar charts for like non-contiguous data, for example. Yeah, and there are a few guidelines how to approach that. Should be easy to understand, so minimal effort. Should be easy to read and quick to read. It should have the maximum information at the lowest amount of ink available. So don't make like gigantic bars, just like make them tiny, so readable essentially. Make a little bit gap in between instead of like stitching them together and stuff like that. Follow common practices. So there are good presentations, for example, by Thorsten Höfler. He has an SC paper on how to do proper scientific benchmarking and communication, and how to like not do fallacies like cutting off your y-axis and other like cheating methods and so on. Avoid ambiguity, use colors when possible, but be mindful that some people are colorblind. And yeah. Don't play those tricks with like log scales or like cutting off something in the middle, or some of the vendors don't give you the information on the x-axis. Some vendors are really bad. So they basically give you a chart where you see like 2 bars, and then they don't say what the scale on the y-axis is, or what even the y-axis is. Sometimes it's just like, hey, here's how much better we are than the competition, and you're like, what are you measuring? Yeah, we can't tell you. Or we have it like very in a footnote under the graph, and you can't see, like you're in a presentation somewhere in the back of the room, and like, what are you measuring? Yeah, typical vendor behavior. Okay. So basically, as a kind of summary, the 10 steps for scientific benchmarks in theory. Initially, you want to state your goal of your benchmarking exercise. You want to list the services and outcomes you want to do. Select the metric. You select the factors you want to study. You select the evaluation method, so either analytical or simulation or real measurement. You select the workload, so the inputs and your application. You can't just select an application without an input, doesn't make sense, or an input without the application, doesn't make sense. So workload is always the combination of input and application. You design the entire experiment. You kind of like estimate how much time you will need. And once the experiment is done, you analyze the result. You document the process. You document the results. You document the outliers. Don't forget about the outliers. Don't just throw them away. Sometimes they're really interesting and they give you a new paper. And then you improve, because you will never get it right the first place. And we're all learning while we're doing it. Okay, that's the theory. I kind of am running over it. When is? I mean, like I can bleed into my like hands-on. That's fine. So well, 45 and then one. It was 90, right? 45 plus 90. Okay, perfect.
Yes.
So I will bleed a little bit into my hands-on. Don't worry. Or should we do a break? Oh, we have a break. Sorry. Then we will finish that later, and we are on a break now. Yes. Yay, break. Sorry.